Next, we have to study the application of Huckel molecular orbital method, that is HMO method, to Allyl system, or how we can apply the HMO method to Allyl system. The Huckel molecular orbital theory is a simple quantum mechanical model that extends our understanding of molecular orbital methods. The Huckel method is generally used for systems of any pi conjugated molecule. The 2p orbital of each carbon atom participating in the pi network is the basis atomic orbitals in the Huckel method. The molecule must be planar, say it is in the xy plane, so that the principal atoms contribute electrons from their 2pz atomic orbitals to the common pi electron pool. Each center is sp2 hybridized and has one unhybridized p orbital perpendicular to the trigonal sp2 hybrid orbitals. The sp2 hybrid orbitals form a rigid unpolarizable framework of equal carbon-carbon bonds. The HMO method is confined to carbon atoms only, and here we ignore the hydrogen atoms. The linear combination of atomic orbitals, that is LCO method, is used to construct each molecular orbital wave functions with undetermined coefficient. This is followed by constructing and solving the secular equations to compute the energies of the molecular orbitals. A computer is deployed to assist the numerical calculation of secular equations for large molecule. Let us take the allyl system. The allyl system has 3 carbon atoms, and the 3 carbon atoms are named as C1, C2 and C3. The HMO, Huckel molecular orbitals of the allyl system, is a linear combination of the pz atomic orbitals of the 3 carbon atoms C1, C2 and C3, and it is named as pz1, pz2 and ps3. Therefore, the Huckel molecular orbital can be written as psi is equal to C1 pz1 plus C2 pz2 plus C3 pz3. Thus, by labeling the carbon atoms 1, 2, 3, the secular determinant for the allyl molecule can be written as determinant of H11 minus ES11, H12 minus ES12, H13 minus ES13, H21 minus ES21, H22 minus ES22, H23 minus ES23, H31 minus ES31, H32 minus ES32, H33 minus ES33, that is equal to 0. By considering the assumptions of Huckel molecular orbital theory, that is H11 that is equal to H22 that is equal to H33 that is equal to alpha, H12 is equal to H21 that is equal to H32 that is equal to H23 that is equal to beta, S11 is equal to S22 that is equal to S33 that is equal to 1, and Sij that is equal to 0. Therefore, the above secular determinant can be transformed into a secular determinant by using the Huckel assumptions. Therefore, the secular determinant can be written as alpha minus c beta 0, beta alpha minus c beta 0, beta alpha minus c that is equal to 0. This equation can be made more simpler by dividing each element beta and substitute alpha minus c divided by beta that is equal to x. Therefore, the Huckel determinant now takes the form determinant of x10 1 x1 0 1 x that is equal to 0. By using the methods of linear algebra, we can solve this Huckel determinant. That is, this Huckel determinant is equal to x is, by solving this, that is x is equal to this determinant is equal to x into determinant of x1 1x minus 1 into determinant of 1 1 0x plus 0 into determinant of x1 1x, that is equal to 0. Therefore, by multiplying these 2 by 2 determinant, we get the solution of x, and by solving this 2 by 2 determinant, we get a polynomial that is equal to x cube minus 2x, that is equal to 0. This polynomial equation has two roots, that is x is equal to either x is equal to 0 or and x is equal to plus or minus a root. We know that x is equal to alpha minus c divided by beta. Therefore, if we have three roots, take one by one. First, we take when the value of x is equal to minus root 2, we get the value of energy E is equal to, that is E1, that is equal to alpha plus 2 beta. This will be the lowest molecular orbital energy and it corresponding to the bonding molecular orbital. When x is equal to 0, we get the value of energy E2, that is equal to alpha. Because alpha is the energy of an isolated p orbital, this corresponds to a non-bonded level. When s is equal to plus root 2, we get the value of energy. It is designated as E3, that is equal to alpha minus 2 beta. Because beta is a negative number, this corresponds to antibonding level. Therefore, the allowed values of pi energy levels are in the order of E1 less than E2, which in turn less than that of E3. Now we have to calculate the HMO coefficient. The secular equation for the Allyl system can be written as C1x plus C2, that is equal to 0, C1 plus C2x plus C3, that is equal to 0, C2 plus C3x, that is equal to 0. This is from the secular determinant. We know that x is equal to alpha minus c divided by beta. For the root, x is equal to minus root 2. This is corresponding to bonding level. By substituting the value of x is equal to minus root 2 to the above equations, we can find out the coefficient. That is, by substituting the first equation, that is root 2 c1 plus c2, that is equal to 0, or c2 is equal to root 2 c1. Then the second equation, here c2 is equal to 0, therefore c2 into c2 minus root 2 c3, third equation, that is equal to 0, or c2 is equal to root 2 c3. Therefore c1, that is equal to c3. From the normalization conditions, that is c1 square plus c2 square c3 square, that is equal to 0. Then write the c2 and c3 in terms of c1 and substitute the value of c1 in this equation, that is c1 square plus c2 square plus c3 square, that is equal to 1. We get for c1 square, that is equal to 1, or c1 is equal to 1 by 2, which is also equal to c3, and c2 is equal to root 2 by 2. Therefore, the bonding Huckel molecular orbital psi1, that is given by the equation, that is by giving the coefficient, we get the Huckel molecular orbital, bonding Huckel molecular orbital as psi1, that is equal to 1 by 2 pz1 plus root 2 by 2 pz2 plus 1 by 2 pz3. Next, we have to substitute the value of x is equal to 0. By substituting this value, we get the molecular orbital corresponding to non-bonding. Here, by substituting the s is equal to 0 to the above equations, we get c2 is equal to 0 and c3 is equal to minus c1. By applying the normalization conditions and writing the c2 and c3 in terms of c1, we can find out the value of C1 as is equal to 1 by root 2 and C3 is equal to minus 1 by root 2. Therefore, the molecular orbital corresponding to non-bonding Huckel molecular orbital, that is psi2, that is equal to 1 by root 2 pz1 minus 1 by root 2 pz3. Next we have to consider the root x is equal to plus root 2. This corresponds to antibonding level. Then by substituting the values of plus root 2 into the secular equations in terms of x, we get the different values of the coefficient as C2, that is equal to minus root 2 C1 and C1 is equal to C3. Therefore, by applying the normalization conditions, C1 square plus C2 square plus C3 square, that is equal to 1, and write C2 and C3 in terms of C1, we get for C1 square is equal to 1, or C1 is equal to 1 by 2 is equal to C3, and C2 is equal to minus root 2 by 2. Therefore, the corresponding Huckel molecular orbital, that is antibonding molecular orbital, that is given by psi3, that is equal to 1 by 2 pz1 minus root 2 by 2 pz2 plus 1 by 2 pz3. Therefore, the three Huckel molecular orbitals are psi1, psi2 and psi3. Psi1 corresponding to bonding, psi2 corresponding to non-bonding, and psi3 corresponding to antibonding. The 3 pi molecular orbitals are analogous to 3 sigma orbitals found in the 3 center 2 electron bonding. Psi1 is bonding, psi2 is antibonding, psi3 is antibonding. The bonding molecular orbital psi has the energy E1, that is equal to alpha plus root 2 beta, has 0 nodes. Here C2 coefficient is the largest. The non-bonding molecular orbital psi2 has the energy E2, that is equal to alpha, has 1 node. Here the coefficient C2 is equal to C3. The antibonding molecular orbital C3 has the energy E3, that is equal to alpha minus root 2 beta, has 2 node. Here also C2 coefficient is the largest. This figure shows the Huckel energy levels of the allyl system. There are 3 types of allyl system. They are allyl carbonium ion with 2 pi electrons, and allyl radical with 3 pi electrons, and allyl carbon ion with 4 pi electrons. The third and fourth electrons in the radical and anion goes into the non-bonding level. The HMO energy levels of the 3 allyl systems are shown in this figure: allyl cation, allyl radical, and allyl anion. Next we have to find out the pi bond and delocalization energies of the 3 allyl systems. For the allyl cation, when we substitute the values, we get the final value as 2 into root 2 beta. Similarly, we get for allyl radical, we get the same value, and also for the allyl anion, we get the same value. Therefore, all these cases, the pi bond energy remains the same. Therefore, the classical structure for the 3 allyl systems are C double bond C single bond C plus, C double bond C single bond C radical, C double bond C single bond C minus, which consists of 1 double bond and 1 single bond. Since the HMO encompasses all the 3 carbon atoms, it may be assumed that the pi electrons are delocalized and the HMO are spread over the entire framework. References: Quantum Chemistry R.K. Prasad, Computational Chemistry Hero Levers, and EPG Padashala, a gateway to all postgraduate courses.